Day 3 of nuclear chemistry, transmutations. Alchemy, a science that was used in the Middle Ages with the goal of changing ordinary metals into gold. I don't know why they want gold. Personally, I would want plutonium, but they didn't know that existed then. Or platinum. Platinum's pretty good too, right? Anyway, let's talk about that. The modern practice of chemistry started in medieval Europe and the Middle East. Why is it the modern practice? Because they were playing around with stuff, with matter. That would be chemistry. So, alchemists in the 16th century believed that by doing certain chemical reactions, you could turn cheap metals into gold. And many alchemists during that time spent lots of lab hours playing around trying to do this. We now know that no chemical reaction can achieve this goal. It's just a Halloween fun time pastime. However, through transmutations, modern chemists can change one element into another. And it's not easily done. So let's define it. The conversion of an atom of one element to an atom of another element is a transmutation. This can occur in two ways. Through radioactive decay, we've talked about that yesterday, and when the nucleus of an atom is bombarded with certain types of particles like protons, alpha, beta, gamma reactions, etc. Many transmutations already occur in nature. Carbon-14 is made from nitrogen-14 in the upper atmosphere. Nitrogen's swimming around, hanging out, having a good time. It spits out a neutron. That means nitrogen is transmutated into carbon. They have the same mass, but one of those neutrons could have been a proton, which it was. So now it's, instead of 7 atomic number, you have atomic number of 6. And a proton. Many other transmutations occur, and they are done in the laboratory. For example, the first artificial transmutation was done by Rutherford. 1919, he found the discovery of a proton. How did he do that? Here's nitrogen. He shot alpha particles at it. He came up with fluorine. 7 atomic number plus 2 atomic number will give you the atomic number of 9. And look, the atomic masses actually work out the same way too. So nitrogen was bombarded with helium, and that nucleus accepted this helium atom, which means it transmutated into fluorine. Transmutation reactions are written using the following guidelines. Make sure the sum of the mass numbers, top left, is the same on both sides of the equation. Make sure the sum of the atomic numbers, bottom left, is the same on both sides of the equation. Be familiar with the following. Alpha is helium, atomic mass 4, 2 protons. This is straight from the periodic table. Same thing with the alpha Greek letter. Here's an electron, no mass, but a -1 charge. It's written the same way as Greek letter beta. Gamma, no mass, no charge. Greek letter Y. Here's a neutron. That's how we write a neutron. Has mass of 1, roughly 1, and charge of 0. A proton, yes, that's hydrogen. Mass of 1 and a charge of 1. Same thing, written as proton right here with a P. Here is a positron. Positrons are just a subatomic particle with the same mass as an electron, so roughly 0, and a numerical equal positive charge. So here, positive. And we write that as beta plus 1 because it's an electron with a positive charge. It's a particle, actually, not exactly an electron. So let's practice some. Identify the missing information. you have Pu. And on this side, you have a neutron, and 242 and 96 was given. So how did Pu go to over here? Well, if you add a alpha particle here, 94 plus 2 gives you 96. Oh, okay. That makes sense. I have a mass number 239 plus 4 would give you 242. Okay, that makes sense. That would be Cm. If you look on the periodic table and find 94, that's plutonium. If you add 2 protons to that, you get curium, Cm. And let's just make sure that our mass numbers match on the left. I have 243 on this side. Over here, I have 242 plus 1 is 243. 94 plus 2 is 96. Plus 0 on this side is 96. So it matches left and right. Let's try this another one. I have uranium. Uranium, 238, 92 specifically. I have, on the other side, CF, californium. Oh, those Californians. Mass of 246 and atomic number 98. So I know that my atomic number has to equal 98 because 98 plus 0 is 98. So this needs to be a 6. That is carbon. Now, what about my atomic mass? Let's see here. I got 246 plus 1. No. Plus 4. So that's 250. So what's 238 plus 12? 250. Write the beta decay for carbon-14. Well, there's carbon-14. Atomic mass of 14, because it told me so. Carbon has 6 protons. Beta decay means I'm going to have an electron, right? What else happens in a beta decay? A neutron breaks down into a proton. So this is the correct way to write beta. We learned this yesterday. How about alpha decay? We also learned this yesterday. Let's look on radon. 222. Here we go. Radon has atomic number of 86. It's also a noble gas, if you didn't know. Alpha decay has got to have helium. So if I added a alpha particle to radon, I would get polonium. So 222, ejected helium, subtract 4, that's 218, right? If I add those together, I get 222. 86, ejected 2 protons, so that's 84. And if you look in the periodic table, that is correct. Elements in the periodic table with atomic numbers above 92 are called transuranium elements. Why are they called that, Mr. Miller? Well, all of these elements undergo transmutation. They do not occur in nature and are synthesized in the laboratory. So yes, mad scientists do exist. It's not just a figment of your imagination. Above 92, we are playing around the lab, creating elements. To synthesize these elements, particle accelerators are bombarded with really fast-moving particles, specifically bombarded into their nucleus. Now imagine trying to shoot a bullet into a nucleus. A nucleus is tiny, 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 tiny. It's not easily done. Here is a particle accelerator. Magnets are used to fling particles through these tubes that you can see here. And they go really, really fast and slam into an atom of our choice that we have put in the pathway of those particles. Let's start worksheet 3.